We're continuing our discussion with thermal expansion, which is this change in size or volume of a given system as its temperature changes. So a change could be an expansion or it can be a contraction. We just call it thermal expansion. So here we have a couple of examples. This is concrete that they have built in such a way, and I'll talk about it in a minute, but so that when there is some sort of contraction or expansion, we don't have roads falling apart. Same thing with the bridges. The bridge here, we have that same sort of thing where we have certain materials together so that it counteracts any sort of breaking of the material. Definitely don't want roads to break, and we definitely don't want bridges to break. So this stuff is very important, especially for engineers. So let's talk about thermal expansion in terms of the calculations. So dL/dt is some change in length per temperature, where L is the length and alpha is the coefficient of linear expansion. So this is expansion in one dimension, linear expansion. Or we can write it as not a derivative, but we can say delta L, or delta length, the change in length, is equal to alpha, which again is the coefficient of linear expansion, times L, the length, times delta T, the change in temperature. And there is a list of thermal expansion coefficients in OpenStax, and I'm just going to go ahead and click on it so that we can view it. Ignore the many tabs that I have open. All right, so if I click on that, it should take me, well, it didn't, but it should take you to table 1.2, thermal expansion coefficients. And so this is the list of expansion coefficients. We have linear expansion coefficient here, and eventually we will look at volume expansion, but we will do that in a minute here. So we have solids, we have a list of the solids, then we have liquids and gases once we get to volume. All right, so going back to our PowerPoint, let us, whoops, didn't need to do that. All right, so let's look at this thermal expansion in 2 and 3 dimensions. So this is our 2-dimensional expansion here. So we can see A and B, that's what those two are. And this has a very similar equation. Notice the similarity. Now we just have area instead of the length. We have an area. Then if we look at 3 dimensions, we have a volume instead. And notice our coefficient of friction is here. It is present, but in our 2-dimensional, we times it by 2. In our 3-dimensional, we times it by 3. That's what this beta is. Beta is equal to 3 times alpha, our linear expansion coefficient. So we have here in C, we can look at the expansion in all 3 dimensions here. Okay, and this is what would happen typically in the real world. We will have 3D expansion. Now with that comes thermal stress, and this stress is a result in temperature changes. And again, like I said before, engineers will try to avoid this by designing components so that they can expand or contract freely. So an example would be in highways, and we see this all throughout the Central Valley. Highways have gaps in between blocks to prevent this thermal stress. So these little gaps will be kind of like cutting up the concrete in a sense, not literally, but that's what it looks like, in order to have these little gaps and prevent this thermal stress and then possibly breaking up the road. Another thing that we use is reinforcing rods or rebar in concrete that are made of steel, since steel's coefficient of linear expansion is close to concrete. And so this helps with that thermal stress as well. What's kind of interesting, just a little tidbit, I worked at a geotechnical engineering firm or place for a while, and they were testing, concrete and rebar, and they were testing how much stress that rebar can be put under before it breaks. And a lot of times they would pass and it would be totally fine, but it's just something interesting to see in real life and to see engineers making these improvements when you didn't think. Some places that you don't think about. You just put a concrete slab down. At least in my mind, you just put the concrete down. But knowing this idea, we have to put that rebar in, and this is exactly why. All right, so let us talk about the mechanical equivalent of heat. So this is the idea that this can change the temperature of a substance by doing work. So a change can happen with the temperature by doing work. This is the transfers energy into or out of a system, and this heat is a form of energy. James Prescott Joule performed these experiments to establish this mechanical equivalent of heat and the work needed to produce the same effects as heat transfer, which is going to be 1 kilocalorie is equal to 4,186 joules. So this was his experiment here. We have a couple of mass weights, and as the masses descended, they would cause the paddles in this jar here to do work on the water and resulted in a temperature increase. So this kind of makes sense. As you agitate something, it should increase in temperature. Now, the agitation would have to be over a longer period of time, but this is something kind of interesting to note, that a temperature change can be done by doing work as well. So here is the heat transfer and temperature change. So heat transfer, Q, is equal to the mass of the substance times C, the specific heat or specific heat capacity, times the change in temperature, which depends the change in temperature. The specific heat depends on the material and the phase that it's in, and there is a table again in our textbook. If I go here, table 1.3, let's pull it up, and it will go over these specific heats. Again, did not take me there, but here it is. So these are the lists of specific heat in different units. So as you may notice, this is actually in joules per kilogram times degrees Celsius, and this one is in kilocalories per kilogram times degrees Celsius. So note those units, okay? When you're going through this, they have solids and liquids and gases as well. All right. We can also describe the specific heat in terms of temperature. So C is equal to 1 over the mass times delta Q over delta T, or we can write this in a I forgot what it's called off the top of my head, derivative form. And so C would also equal 1 over m dq dt. Okay, it's just some change over the change in heat, or the heat transfer, over the change in time. Now, I need to talk about, or I need to tell you about the calorimetry problem. Now, objects at different temperatures are placed in contact with each other, but are isolated from everything else. These things are allowed to come into equilibrium. And in this case, we have something called calorimetry, which is the use of a calorimeter to make measurements that are like the heat or the specific heat capacity. And a calorimeter is a container that prevents any heat transfer in or out. So commonly in lab, we will see maybe a styrofoam cup as being the container to prevent heat transfer in or out. Styrofoam is a really good um, source or a really good calorimeter to use um, because if you've ever had a styrofoam cup, you can never really feel whatever the heat or the cool um, liquid is inside of like the cup, right? Um, and so like it keeps ice really cold or it keeps your warm drink really warm. So that's typically used. And the heat of the cold plus the heat of the hot should all equal 0. So it's kind of like summing all your forces and they should equal 0. It's a very sort of similar concept with all of your heat. Your cold heat and your hot heat should equal 0. Okay? All right, so I'm going to pause here and then we'll continue with our phase diagrams and looking at phases.